Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In this video, I want you to focus on something that, in my experience, most students struggle with: concentrations. So, if you're ready to concentrate, get yourself a drink, sit back, and let's make a start. When we define a concentration, we are simply saying how much of one thing there is compared with how much there is of something else. So we need at least two things to define a concentration. Usually, but not always, there is more of one of the two things than the other. We call the majority component the solvent and the minority component the solute. To define a concentration, therefore, we simply say how much solute there is for a given amount of solvent. When a solute is dissolved in a solvent, we end up with a solution. For instance, if we dissolved 1 gram of aspirin in 1 litre of water, we would have a solution of aspirin with a concentration of 1 gram per litre. The beauty of defining concentrations like this is that the total size of our sample doesn't matter, because a concentration term is a ratio. We could dissolve half a gram of aspirin in half a litre of water, or 10 grams of aspirin in 10 litres of water. They all have a concentration of 1 gram per litre. I think this is one of the big errors that students make. They forget that concentration is independent of sample size. If you start with a litre of a solution of concentration 1 gram per litre and use half of it, such that you have half a litre left, it still has a concentration of 1 gram per litre. If, however, the question is how much aspirin do you have, then in 1 litre of solution you have 1 gram, and in half a litre you have half a gram. So you must remember that while the concentration of a solution is independent of the amount you have, the actual quantity of material you have is dependent on the amount you have. As the concentration of a solution changes, so its properties also change. Imagine I had 3 glasses, each containing the same volume of water. If I added different amounts of squash, 1 milliliter, 5 milliliters, and 10 milliliters, you can imagine that the final colour of the solutions will deepen as the amount of squash increases. In other words, the intensity of the colour is a function of the concentration of, in this case, squash. I hope you can also see, therefore, that we can use this relationship in reverse. If we measure the intensity of the colour of a solution, we can know its concentration. This is the basis for how spectroscopy is used to measure concentrations. There is one really important aspect of concentrations that we must talk about: units. Units. Units are very important, and it really helps if you understand them, particularly because different units are used in different areas of science, and being able to convert between them is really important. We have already used one type of unit in this video, grams per litre. This type of unit is known as weight volume because, well, it expresses a weight in grams per unit volume, litres. This works fantastically when the solute is a solid and the solvent is a liquid, which is nearly always the case in pharmaceuticals. Sometimes the solute may be a liquid, in which case we can use milliliter per litre for our concentration, or volume. We can also have grams per kilogram, weight, although the last option, milliliter per kilogram or volume weight, is not usually found. I think these are the easiest units to understand, which is probably why they are commonly used in healthcare. You may also have heard of a slightly similar type of unit, percent weight volume, or percent volume, and so on. This is very similar to what we've already seen, but being a percentage means expressing the amount of solute per 100 millilitres of solvent, not per litre, as there are 1,000 millilitres in a litre. So, if you have a solution of 10 grams of solute per litre of water, then in 100 millilitres of water you have 1 gram of solute. Both terms are divided by 10. 1 in 100 is 1%, so the concentration is expressed as 1% weight volume. Similarly, 20 millilitres of solute in 1 litre of solvent would be expressed as 2% volume to volume. Have a practice at converting concentrations between weight volume and percent weight volume. It will help you a lot in the long run to get these conversions sorted in your head. Now, although the pharmacy world loves weight and percent concentrations, chemists are a funny bunch. And I should know, I am a chemist. And they prefer the concept of moles. Never has one word struck such fear into the hearts of students. Well, maybe exam and fail, but you know what I mean. The word mole simply refers to a number of molecules. 1 mole of any compound always contains the same number of molecules. And how many molecules is that, I hear you ask? Well, it's a very big number because molecules are very small. It's 6.023 times 10 to the power of 23. That's big, and it's a special value we call Avogadro's number. A much easier way to work with moles is to remember that 1 mole of a compound will weigh its molecular weight in grams. So 1 mole of water, which has a molecular weight of 18, 1 oxygen at 16 and 2 hydrogens at 1 each, will weigh 18 grams. 1 mole of aspirin, molecular weight 180, will weigh 180 grams. If we have 1 gram of water and 1 gram of aspirin, then there are 10 times more water molecules than aspirin molecules because the molecular weight of aspirin is 10 times that of water. Similarly, if we have 18 grams of water and 180 grams of aspirin, there are exactly the same number of water molecules as aspirin molecules because we have 1 mole of each. I do accept that the mole is a much more complicated concept than weight, but it will make sense eventually. To express a concentration in mole terms, we state the number of moles per litre, which we call molar. Therefore, a solution containing 1 mole of solute per litre of solvent is 1 molar. Why do chemists insist on using moles? That is also a good question. It's because, as I hope you can see from what I just said, that when comparing 2 compounds together, the number of moles is independent of molecular weight. So by keeping the number of moles the same, the actual number of molecules is the same. When we use percent weight volume concentrations, for instance, we often forget that 2 different compounds in solution, both at 1% weight volume, will actually contain different numbers of molecules. The same 2 compounds in solution at 0.1 moles per litre will contain the same number of molecules. This is not so much of a problem when the molecular weights of the compounds are similar, but it can become so as the molecular weights become very different. For instance, when comparing a low molecular weight drug with a high molecular weight polymer. You can convert between moles per litre and weight volume if you know the molecular weight of the drug. For instance, I noted earlier that the molecular weight of aspirin is 180. Therefore, a 1 molar solution of aspirin will contain 180 grams of aspirin per litre, or is 18% weight volume. There are 2 more commonly used concentration terms that I should mention. One is parts per million, ppm, or parts per billion, ppb. These do what they say on the tin. A solution of concentration 1 ppm means 1 molecule of solute per million molecules of solvent. As you might imagine, these concentrations are very low. 1 ppm would be 0.0001% weight volume, for instance, so are commonly used for describing trace amounts of material. Finally, there is mole fraction. Since students frequently find the concepts of both moles and fractions confusing, this is often a tricky one. Mole fractions are not actually that bad, however, once you are okay with moles. A mole fraction simply means what fraction of the total number of moles in a solution is solute. If we take aspirin again, 1 mole of aspirin weighs 180 grams. 1 litre of water contains 55.56 moles of water. I will let you calculate that for yourself. So a 1 molar solution of aspirin would contain 180 grams of aspirin per litre of water. In terms of moles, there would be 1 mole of aspirin to every 55.56 moles of water. The total number of moles is therefore 56.56. The fraction of those moles that are aspirin would be 1 divided by 56.56, or 0.018. Similarly, the mole fraction of water would be 55.56 divided by 56.56, or 0.982. Note that these values should sum to 1. If they don't, you've calculated your concentrations incorrectly. Handy tip for your exams there. Okay, that was a lot of information. I know that students find concentrations tricky, especially moles and converting between units. If you remember that 1. Concentrations all express only a ratio of solute to solvent, and 2. Moles is a technical way of counting molecules, you should be fine. I highly recommend practicing converting concentrations between units, and you will soon find it second nature. Thank you for concentrating. If you found that useful, please hit the like button and consider subscribing. It really helps the channel. Otherwise, thank you so much for watching, and I'll see you again soon.